In this problem, we have to solve the differential equation given by tangent of 1 over x raised to the power of 5 multiplied to derivative of y with respect to x equals to x cubed. This given differential equation, although it looks non-linear, but is actually a linear differential equation. And how do we do that? How do we check that out? So let's try to simplify it. We're going to take the arctangent or tangent inverse on both sides of the ordinary differential equation, and that should give us tangent inverse of 1 over x raised to the power of 5 times derivative of y with respect to x equals to tangent inverse of x cubed. Now on the left hand side, the tangent inverse of 10 will nullify each other, and that should give us 1 over x raised to the power of 5 times dy over dx is equals to tangent inverse of x cubed. Now this is a simplified linear differential equation. Now what we can do, we can isolate the differentials, and that should give us dy is equals to x raised to the power of 5 times tangent inverse x cubed dx. So this is in the separable form. Now we are going to integrate it both sides. So we will get integration dy is equals to integration of x raised to the power of 5 times tangent inverse x cubed dx. Now we will do a little bit of algebraic manipulation here. So x raised to the power of 5 can be written as x cubed times x squared, such that we can rewrite this integral as integration of x cubed times tangent inverse x cubed times x squared dx. We have done this so that we can replace x cubed with another variable u and differentiate both sides with respect to x, and that should give us 3x squared equals to du over dx, or simply x squared dx equals to 1/3 of du. So our integral now becomes y, which is the integration of dy. It will be equal to integral x cubed will become u times tangent inverse u, and x squared dx gets replaced with 1/3 of du. Now we have to solve this particular integral by parts. For that, we are going to consider tangent inverse of u as the first function and u as the second function. So let's start with integration. So we have y equals to 1/3 multiplied to the first function, tangent inverse of u, times integration of the second function, u, which is u squared over 2, minus integration of derivative of the first function, which is tangent inverse of u, so that is 1 over 1 plus u squared, times integration of the second function, which is u, so that will be u squared over 2 times du. That gives us 1/3 of u squared over 2 times tangent inverse of u minus half times integral u squared over 1 plus u squared du. Look at the integral, we have u squared in the numerator, so we are going to add and subtract 1. Now finally we are going to get 1 over 6. So here we have taken out the factor 1 over 2 from inside the parenthesis and multiplied it with 1/3. So that should give us 1 over 6 multiplied to u squared tan inverse u minus integration of, so here the integral can be written as 1 minus 1 over 1 plus u squared du. Carrying out the integration, we have 1/6 times u squared tangent inverse of u minus integration du. Negative times negative will become positive. Integration du over 1 plus u squared, which is equals to 1 over 6 times u squared tangent inverse u minus integration of du will be u, plus integration of du over 1 plus u squared will be tangent inverse of u, plus the constant of integration c. Now we are going to replace the value of u with x cubed. So we get y equals to 1/6 of x raised to the power of 6. Because we have u squared, so x cubed squared will be x raised to the power of 6 times tangent inverse of x cubed minus x cubed plus tangent inverse of x cubed plus c, and this is going to be the solution to the given differential equation.